morning, everyone. Today I will present to you our work on online mechanism design with predictions, and this is joint work with Balkanski, Vasilis, Gkatzelis, and Xizhi right over there. So we will be focusing on the setting of online auctions. So let's say that we have an item that we want to sell, and instead of all the bidders being present at once and giving you all their bids at once, as in the offline auction, instead all of your customers are coming and going over time. And as they're coming and going, you have to decide what price to present to them. And so this is an increasingly prevalent setting with the rise of things like online shopping and platforms like eBay, but perhaps a more concrete example is the car dealership. So we have a car salesman here who wants to sell a specific model of car. And throughout the day, he has customers coming in, and he has to decide what price to offer to each customer. And in order to maximize revenue, he might actually choose to present different prices to each customer and changing the price in order to incorporate new information he's getting in terms of what people are willing to pay for this item. And so we can formalize this model, which was first presented by Xizhi, Steinberg, and Parks in 2004. So we have our car, and we have a time horizon over which we want to sell the item. And so we have a customer, or as we call them, a bidder, arrive. And so he has some valuation for the car that represents how much he thinks the car is worth. And he arrives, announces his arrival, and then at some point he will depart and announce his departure. And so over time, we have bidders arriving and departing. We don't know the value of the people coming afterwards. And so we have to make decisions without the full information. And the strategic element comes from the fact that bidders can delay their arrival, they can choose to leave earlier, and they can also misreport their value through their bid. And so an instance in the setting is defined by a set of values and a set of active intervals. You can think of these as being chosen adversarially. And in order to create the actual bidder information, we match the values onto the active intervals randomly. To give you some intuition about this, if you're familiar with the classic secretary problem, this is a generalization of the random ordering. So if our active intervals were disjoint, then the bidders would just arrive in some random order. And so the auctioneer has to decide who to give the item to and at what price P, only using the information from the bidders that have already come. And so the bidders here are trying to maximize their utility. And so this is what we would expect it to be, which is the value of the item, what they think the car is worth, minus the price that they would pay. If they are allocated the item during their active interval, they can't gain any value from getting the item if they're not actually there, and it's zero otherwise. And so the goal as the auction designer is to design an auction that is both value and time strategy proof. So there is no way for bidders to increase their utility by misreporting either their value or their arrival time or departure time, and do so in a way that maximizes the expected revenue, where the expectation here is over the random matching and any potential randomness in the auction itself. And so maybe the first question we should ask ourselves in this setting is, what can we even aim to get in terms of revenue? To answer this question, we can go back to the original offline auction setting, where we have all the bidders present at once, and we receive all the bids at once. It's well known in this setting that it's impossible to extract the revenue that approximates the highest value. We denote this V1. And intuitively, the reason for this is if we want to get revenue approximating V1, we have to sell to the highest bidder, and the price that we give them is going to be dependent on their bid. So they're going to want to make that as low as possible. But we know that the second price auction, also known as the victory auction, can achieve revenue equal to the second highest value, V2. And so because of that, V2 is very often used as a benchmark for the performance of auctions. And this is exactly what Xizhi all do in their paper on online auctions. So with respect to this benchmark V2, they show the possibility of achieving a 1/4 approximation. And they also show that it's impossible to achieve a 2/3 approximation. So now that we know what is possible in the online setting, we apply the width prediction framework to this. So on a high level, the idea of the width prediction framework is that in the real world, you usually have some sense of the instance that you're looking at. And the way that we incorporate this is we assume you have a black box prediction with regards to the instance. We make no assumptions on the quality of the prediction or the distribution of this prediction. And we want to use this prediction in a way that improves the performance of our algorithm. And so this gives rise to two metrics. The first is consistency, which is the performance, whether you use competitive ratio or approximation of your algorithm when the prediction is correct. And the second is robustness, which is the performance of your algorithm given any potentially arbitrarily bad prediction. So this line of work was first and is most often applied to online algorithms, where the prediction gives you information about future values. But more recently, it has also been applied to mechanism design, where the prediction gives you information about the private values of the agents that you otherwise would be unable to notice. And what we do in our work is we take these two sources of missing information and we combine them and we initiate the study of online mechanism design with predictions. And the way we do this is we focus on online options with predictions. So the prediction that we use in the setting is a prediction with regards to V1, what we think the highest value is going to be. And so we can now define consistency and robustness in the setting. So we say an option is beta robust if for all instances and all predictions, it achieves an expected revenue of at least beta times V2. So you see here, we're using that previously used victory option benchmark or V2. And then we say an option is alpha consistent if for all instances, and when the prediction is correct, it achieves an expected revenue of at least alpha times V1. So notice here, we're actually using a different benchmark than the victory option. We're using a stronger benchmark. And we believe that we are the first to actually use two different benchmarks for consistency and robustness. To give you a sense of why we do this, let's look at two simple approaches. The first is if we just trust the prediction and always post it. If the prediction is correct, eventually the highest bidder is going to arrive. We sell the item to him at the price equal to V1, and we can actually extract the optimal revenue, what was impossible in previous settings of both the offline and online auction. However, if let's say the prediction is too high, none of the bidders would actually accept the price, and so we never sell the item and we get zero revenue and therefore zero robustness. On the flip side, we can just ignore the prediction and use the previous 1/4 approximation option given to us. And this gives us 1/4 robustness. However, because our consistency is against that V1 benchmark, if V1 is magnitude larger, let's say, than V2, then that 1/4 guarantee is negligible compared to V1. And so we get essentially zero consistency. And so you can see that in this graph, we have consistency on the horizontal axis and robustness on the vertical. What we can do with these two simple approaches, if we just pick one randomly, then we're going to fall somewhere on this line. But the question that we want to ask in our research is, can we do better than this? Can we push that line further up and get better robustness and consistency? In other words, what is the optimal consistency robustness trade-off achievable? Which brings me to our results. So first, we present an auction that is both value and time strategy proof and achieves alpha consistency and 1 minus alpha squared over 4 robustness. So you can think of alpha as a parameter that represents how much you trust the prediction. The closer to 1 it is, the more you trust the prediction. And so what this trade-off looks like visually is if we go back to that original picking between two simple approaches, our option is represented with this green line. And so you can see we do significantly better than picking between the two simple options. And to complement the result of our auction, we also provide an extension of this that achieves guarantees as a function of prediction quality. So you can see consistency and robustness is only in terms of the binary of whether the prediction is correct or incorrect. It doesn't take into account if the prediction is close to correct. And so we can actually get guarantees against that V1 benchmark, even if the prediction is slightly off. And I'm happy to discuss that offline. But to complement the performance of our auction, we also present some type counts. So the first one is for a large family of auctions, the trade-off that we achieve is actually typed. In other words, we cannot hope to do better than this line for this family of auctions, and our auction is optimal. Now, if we take a step back from the with prediction framework and recall that in the original online auction setting, previous work has shown that it's possible to achieve a 1/4 approximation and it's impossible to achieve a 2/3 approximation. So there was still a large gap between them. So we actually closed that gap by showing for a large and very natural family of options, that 1/4 approximation is tight. And so even in the original online auction setting, there's still very interesting questions in terms of what is possible and impossible. And so first I will present our option, which we call the three-phase option. We will focus on the case where the active intervals are disjoint for simplicity first. And it's three phases. And when the active intervals are disjoint, this becomes a posted price option. So a bidder arrives, we post a price, they tell us their bid, and if their bid is at least as high as the posted price, we give them the item and they pay that posted price. And so the first phase we call the learning phase. We never allocate the item, we're just observing people's bid, and this is equivalent to posting infinity. The second phase is the prediction phase. And we test the prediction by posting the maximum of the prediction and the maximum bid so far, which we denote Vmax. The reason we do this is if Vmax is larger than the prediction, then we know the prediction is wrong, then there's no point in posting it. And finally, the last phase, we stop using the prediction and just post Vmax. You can see a clear connection here to the secretary problem. And the way that we choose the length of each phase is we use that parameter alpha. And so we switch phases after seeing a certain number of bidders. And how we decide when to switch, we calculate using alpha. So what this actually means in terms of the proportion of bidders that fall in each phase is the following breakdown. And so you can see the consistency guarantee comes from the probability of the highest bidder arriving in phase 2. So when we're actually posting the prediction, which is with probability alpha. The robustness guarantee is a little bit harder to see, but intuitively, the idea comes from we want to post price equal to Vmax to the highest bidder, having already seen the second highest bidder. We're posting a price equal to V2 to someone who would accept that. And a lot of the subtlety from our auction comes from dealing with overlapping intervals. So if we go back to the general case and allow the overlapping intervals, we first break our auction down into an allocation rule and a payment rule. So to determine who gets the item, we still have our three phases, but now we are switching phases after a certain number of departures, a certain number of bidders that have departed. And now instead of a posted price, we have a threshold price, which we denote tau. And very importantly, the threshold price is determined by the values of bidders that have already departed. If a bidder is currently present, the threshold price that he sees is not determined by his own bid. This is very important for strategy proofness. And so we pick a winner I star when we have an active bidder that has value at least the threshold price. If there are multiple such bidders, we determine priority by earliest arrival time. And then we give the winner the good at the time of their departure. So you can see all of these choices, like switching phases after a certain number of departures, determining priority by arrival time, these are all chosen in order to maintain both value and time strategy commitments. So once we have a winning bidder, we have to decide what they pay. In most cases, they're going to pay that threshold price tau, but there's a difficult case when the bidder arrives in phase 2 and is still active in phase 3. The reason for this is because the price might actually drop in between phase 2 and phase 3. So I won't go into the details of when this happens, but essentially in certain situations, depending on the other bidders' arrival times, departure times, and bids, there might be an incentive for the winning bidder to misreport in order to try to gain that lower price if they think that they're entitled to it in some way, or they think that they're able to win it over. And so all of these little details that I'm not going over on the screen gives you an idea of how we had to carefully design the auction in order to get this guarantee, which is that our three-phase auction is both value and time strategy proof and achieves that trade-off that I showed earlier. And now to complement this, we prove a tight bound that matches our auction for the following family of predictions. So we define a family of auctions known as the prediction or previously seen auctions, which does the following. When it sees a bidder I, it posts a price P equal to either infinity, just observing the bid, the prediction, or some previously seen value, anything you've seen before. And so the choice of what to post for each bidder I has to be chosen at the start of the auction. And we note that this family of auctions includes both our auction and the previously presented auction. And so what we can show, and I won't get into the details of the proof, is that no auction in this family of auctions can achieve a trade-off better than what we achieve. That this line is tight and that our auction did not. Now, if we return again to the without prediction setting, where we have that gap between the 1/4 possibility and the 2/3 impossibility, we now prove a tight bound for the following family of auctions, which we call the up to max seen so far auction. So in this family of auctions, for each bidder, you can post a price P equal to either infinity or any price that is at most the maximum previous bid. So the only thing that you can't do is post a price higher than all of the values you've seen so far. And so I will give you a brief proof. So there are two ways to gain revenue. You sell to the highest bidder or you sell to anyone else. Most of the technical complexity of our proofs comes from dealing with this first case. So what we are able to prove is that the expected revenue from selling to the highest bidder is bounded above by 1/4 times V2. I'm going to throw out just a few techniques. So first, we reduce to the ordinal problem, where decisions are made just in terms of the relative rank of the bidders, not their actual values or bids. And we do this using a technique that comes from a previous EC'19 paper with regards to the secretary problem, where they use Ramsey's infinite hypergraph theorem. I know it seems out of left field, but it works. And they are able to take the value secretary problem down to the ordinal secretary problem. So once we reduce to the ordinal problem, we can find a linear program representation of it. And we use duality to bound the optimal value of the ordinal problem. And in doing so, we bound the optimal value of the original revenue problem, which is where we get the bound. And just one thing to note is that our setting is similar to the secretary problem, which is why we are able to use the techniques from this paper, but we have the added challenge of revenue maximization and strategy proof. So once we get the bound on selling to the highest bidder, we can also show that we get negligible revenue from selling to anyone else. And so this together gives us our theorem, which is that no auction in this family of auctions can achieve expected revenue higher than 1/4 times V2. And so now we're closing that gap between what we know to be possible and what we know to be impossible. And so to conclude, what we have shown is we have presented a three-phase auction that is strategy-proof and achieves a good consistency robustness trade-off. And we have provided tight lower bounds, one in the with prediction setting that matches the consistency robustness trade-off of our auction, and one in the without prediction setting that matches the performance of a previous auction. And so I will leave you with two open questions. The first is, can we apply this with predictions framework to the K item online auction? So we have K copies of the same item. And the second, and we conjecture that this is true, which is the 1/4 approximation tight for all without predictions auctions? So thank you for your time, and I am happy to take questions.